Welcome to today's video. Today we're going to learn about orbital mechanics. That is, what are the trajectories that planets around stars or satellites around planets follow in general relativity and how they compare with the predictions of Newtonian gravity. Alright, let's begin with it. Solving for the orbital mechanics of a particular gravitational scenario is finding the geodesics associated with that scenario. We want to be able to know what are the orbits around a planet, for example. If you want to brute force those trajectories, what you need to do is to find the geodesic equations and solve the geodesic equations. And that's no small feat. In general, that's something that we won't do. We will try to avoid solving the geodesic equations, even using them. There's only one time to work with orbital mechanics that we're going to use the geodesic equations, and it's now. Basically, geodesic equations, as we saw, have this form, and you can tell that these equations that I give you have the form of geodesic equations, that's in like second derivative of t, that's with mu equals to t, and then crossing derivatives here, first derivatives. Then this is the one with mu equals r, this is the one with mu equals theta, and this is the one with mu equals phi. You get second derivative of theta, second derivative of phi, second derivative of r, second derivative of t. So these are the geodesic equations for the Schwarzschild metric, and solving them will give you the trajectory of all the geodesics, all the possible orbits. Then you give initial conditions, and then it will tell you what orbits, whatever satellite or thing orbiting will follow. Be it null geodesics, like for lights, or be it time-like geodesics for anything else, things that have mass. Now, we're not going to be using these to solve orbital mechanics because we have, luckily, Killing vector fields. And because we have Killing vector fields, we're going to have conserved quantities along geodesics that we're going to use the same way that you use conserved quantities to solve in mechanics without having to compute Euler-Lagrange equations. You would be able, here we're going to be able to use conserved quantities to solve for the geodesics without having to go directly to the geodesic equations. There's one we're going to use though. Let's check the solution. Theta equals pi over 2. So theta exactly equal to pi over 2. So that would be an orbit that is in the equatorial plane. I don't know what it does in the equatorial plane, but it isn't contained in the equatorial plane. We can actually check that this thing is a solution of this equation, right? This thing is a solution to the equation that is giving me theta. You can tell this is 0 equals 0. And in fact, existence and uniqueness theorem tells me that this is the only solution that exists from the initial condition theta tau equals 0 equals pi over 2. So this is telling me that if an orbit starts in the equatorial plane, remains in the equatorial plane. That's the only way, the only time that we're going to use these equations in this course, in practice, to tell us that, oh, interesting, the problem simplifies a lot. All right, but with a loss of generality, I can say in that statement, because the equatorial plane, I can switch it by doing rotations, that tells me that an orbits in Schwarzschild metric are contained in planes. That is something that was also true in Newtonian mechanics. Orbits are contained in planes. You have a very similar result in Newtonian mechanics. But there's no reason a priori why that would be true. Maybe orbits are not contained in planes. They move crazily in general relativity. Well, no. In the Schwarzschild background, orbits are contained in planes. This is what it tells us. Orbits are contained in the equatorial plane, and with a loss of generality, I can get the plane of motion, a change of coordinates, and make that the equatorial plane. Because if not, it's just they don't remain in the equatorial plane because you chose poorly your equatorial plane and you have a tilted orbit. Just get it in the equatorial plane. Now, after knowing this, then we don't need the geodesic equations anymore to solve for the orbital mechanics of things orbiting around planets. Let's see why. Alright, so if we're not going to use the geodesic equation, what are we going to use? We're going to use the conserved quantities. Remember that when we have a Killing vector field, the contraction of the force velocity of a particle moving in a geodesic and the Killing vector field is a conserved quantity along the geodesic. We proved that in the last topic in differential geometry, right? When we proved that the Killing equation implied that. All right, so here we have two isometries, two Killing vector fields, one the direction of t, the coordinate of time for an observer at infinity, and one in the direction of phi, the coordinate phi, the angular coordinate phi, for an observer stationary at infinity. Okay, so I get the force velocity of a particle that I call dt d tau, dr d tau, d theta d tau, d phi d tau, parameter in terms of the proper time of the particle. And then I say that the contraction of the Killing vector field k with the force velocity of a particle following a geodesic, I call it E, and I know that E is conserved along geodesics. And the one with S, I call it L, and I say that L is conserved along geodesics. What do they represent physically? Well, E is related with time translational invariance at infinity. So E would certainly be a way of an energy in a way, but we have to be careful because while every observer would agree that this quantity is conserved along the geodesics, what they may not agree is that that is an energy. They would agree that that is an energy from the point of view of somebody stationary at infinity. So that E would be the energy, the mechanical energy. You will see how it actually plays the role of mechanical energy. The mechanical energy of the orbit for an observer at infinity, or something proportional to the mechanical energy of the orbit for somebody stationary at infinity. Remember, it would not be interpreted like that as for any other observer. Any other observer would say, yeah, it's the mechanical energy, but as seen by somebody stationary at infinity. Then the conserved quantity associated with the Killing vector field S is related with the conservation of the Z component of angular momentum from the frame stationary at infinity, if you want. So it's energy and angular momentum conservation from the point of view of a frame at infinity, okay? But it's conserved along the geodesics, okay? All right. Well, with these two quantities, we can obtain equations of motion that will give us the orbits that the object following geodesics follow, right? So let's use them. If we compute explicitly what is the value of those constants for a given geodesic, we know that it's going to be the contraction of the Killing field with the for velocity for each of them. Let's say for the Killing vector field partial t, then we get this contraction. Of course, the Killing vector field partial t only has one component in the t component, all the others are zero, so we only get gtt kt ut. That gives me minus, directly from that, this is the component of the metric, 1 minus 2gm divided by r multiplied by t prime, okay, or t dot, sorry. All right, so the same with the contraction of S and U, the other Killing vector field, so I can compute the conserved quantity L, and the conserved quantity L will be same thing. There's no components other than the phi component, so that survives is the g phi component, and therefore what we get is r squared sine squared theta phi dots, okay? So now that I know the value of those conserved quantities, let me put them here, and let's apply them to solve the geodesic equation. And then we're going to replace these equations, these expressions that I already stored here, for the normalization condition for the for velocity that we knew from before. Remember, the non-dirty way of doing things. All right, this is the normalization condition. Now, in this normalization condition, remember, all that I did is that the norm of the for velocity is equal to -1. So I expanded the norm of the for velocity, this is the for velocity, and equated to -1, because we're talking about massive particles, orbits for massive particles. We will discuss massless later. Okay, the orbits of massive particles are anything that is not light, massless. What would it look like moving around a planet that is generating the curvature of space-time here in this Schwarzschild metric? All right, so the one thing that we can use right away is say, okay, without loss of generality, because I know that all orbits are contained in a plane, let me place the orbit that I'm going to consider in the equatorial plane. So let's set theta equal pi/2. All right, and I know the orbit will be contained there and won't escape. That is nice because it simplifies this to 0. All right, wonderful. Now the next thing we're going to do also simplifies this to 1, like that. Because again, the sine square of theta is equal to 1 in that case. All right, next thing, let's introduce the conserved quantities. Look, L, I'm going to write L here again because it simplifies again here to just to be equal to r squared phi dot. Then we realize that this quantity here is nothing but L squared divided by r squared, right? And we also check in here, we see that this quantity here, it's equal to, let's just write this quantity here, this is E squared multiplied by 1 minus 2gm r to the -1. So we can introduce these conserved quantities and look at that. The conserved quantities remove the derivative of with respect to proper time of t and the derivative with respect to proper time of phi. Same as you did in mechanics, remove some of the derivatives of the coordinates that you want to solve for in the trajectory using conserved quantities. So I got rid of these two, introducing the conserved quantities. All right, I can now simplify this equation quite a lot. Look at this, there's a common factor between these two, right? I can actually multiply everything by the inverse of that common factor. And I can simplify the equation and write it like this in a way that should look more or less familiar. Let's see. This expression. So look at this because that's going to remind you of something. I wrote minus c squared plus r dot plus this term here. Let me call this term v of r. And I can write it like this. And that probably reminds you of something. Something that looks like the equations in mechanics. When you are in Newtonian mechanics, you say for an orbit, I have something like kinetic energy that goes with the velocity square. Something like potential energy. And the sum of the two is conserved, and I call it mechanical energy of something. Actually, if I want to make it, so this is V of R, if I want to make it very parallel to the Newtonian mechanics version of it, let me write the next line here. I define this epsilon here as 1/2 of E squared, and then I write it literally as the expression, all this expression here would be the Newtonian mechanical energy, you see? Because this is for a particle of mass 1. There is an origin of potential. This is the Newtonian potential with the gravitational part and the angular momentum part. And then you see that we have a relativistic term that changes. What changes, keep in mind that there's no approximations made so far. This is literally, you can tell that there's a Newtonian, there's a mechanical energy in the Newtonian sense of the orbit. You see mechanical energy, kinetic plus potential energy. And then there's a correction that comes from relativity, but not in a perturbative kind of way. This is exact. And you can tell already how, two things you can tell. You can tell that for radiuses that are very large, this term is suppressed, right? And then you get the Newtonian one when you're far away. When the radius is when we're very close to the scales of the Schwarzschild radius, when you're closer to the distribution that generates the gravitational field. Or, important, when your angular momentum is huge, you see here, you cannot separate high velocity to be very relativistic from high intensity of gravitational field. They're both in this term for the orbits. This one is kind of what we would say, going fast. Maybe that's what they refer, again, wrongfully, as the special relativistic contribution to it. And and the one that comes when you're close, right? The one that comes when you're really large angular momentum would give you a relativistic correction. Also, the one that comes when you are very close to, because the action very close to the source of gravity. So this relativistic correction, it's what the difference here. This is, I think, a beautiful expression, because you get the mechanical energy for an orbit. You get it as the Newtonian part plus the relativistic part, and the relativistic part, of course, unifying the contributions from all. There's no such thing as special relativistic contribution and general relativistic contribution. There are only relativistic contributions, or general relativistic contributions. Is not called general because it was dark that night, or they run out of ideas. It's called general because it encompasses everything in special relativity plus gravity. Now, this is actually pretty cool, and the fact that we can write this kind of a mechanical energy conservation kind of equation allows us to do and solve what the orbits would be like, and the difference between Newtonian orbits and general relativistic orbits in Schwarzschild. Let's do that with plots. All right, I have here the equation of motion for the radial coordinate written in terms of the mechanical energy, what plays the role of the mechanical energy, and the potential. Now, I expanded the potential in these three terms. The origin of potential is 1 here, but let me call it V0, it's an origin of potential. And I wrote in red the Newtonian terms, and this is the relativistic extra, what relativity, general relativity adds to orbital mechanics. Now, let's analyze the kind of orbits that you can have. The potential looks like this. The potential has, if L is large enough to have this dip, of course, this has to be large enough in order for this term to actually create a maximum and a minimum here. You're going to have that the potential, of course, at very short distances, the relativistic term dominates, and it takes it to minus infinity. Then in intermediate distance, it's going to start growing like 1 over r squared, that dominates over the r cubed, and then it starts, getting here and growing. But then at larger distances, larger r's, this term kicks in, that is negative, so it brings it down again, so you create a maximum here. And then finally, for large enough r's, the origin of potential is the only thing that survives. All the terms are negligible or become negligible, and then of course that means that you go back to the asymptote. So that is the kind of function that we're plotting here. Now, I plotted in red the Newtonian potential. You can tell the Newtonian potential is identical for large radiuses, right? And then when I try to represent with my drawing skills, that is a little bit above the relativistic one, and until the term with the Q kicks in, which is very different. You see this one grows up to infinity, whereas this one goes to minus infinity. That's the main difference. Now, the zero of this potential is 2gm, okay, which is the scale of the Schwarzschild radius. And we can analyze now what kind of orbits we would have and what is the difference with Newtonian mechanics. This is very nice because we can do a scattering diagram here. Now we can say, depending on the E, coming in with different energies would be in here. I can write a horizontal plane of energy here, and it would tell me what would be the trajectory of the particle scattering with this potential, the same way that you've done in your mechanics. So let's start with this point here. What happens if I start here? That means that I will have an energy E like this. So E is equal to that. Well, if you're there, you can tell this is a radius R0, and you can tell that in that case you're at the minimum of the potential. So if you were a little ball, it would not move, you will stay there. So if you're at the minimum of the potential, you stay at the same radius. What does that mean? Well, that means that in general relativity, you have, if this is the planet, you have this kind of orbits that are circular. So you'll be doing like this. This is constant radius, and that means at the minimum of this potential, you have circular orbits. Circular orbits do exist in general relativity. Nice. Not only that, there's a whole region. Say that you have this energy, right? Say that is the energy that you have. So if you're here, you're gonna start oscillating like that between these 2 points of the potential, and that is an R min and an R max. And what is that? What kind of orbit is that? Well, that orbit would be something like that, like an elliptical orbit, the equivalent to an elliptical orbit in Newtonian mechanics. You go from an R max to an R min, like that, so you go like It's not quite fully an elliptical orbit in the sense that it would be if you were that, because that's what you get with Newtonian mechanics. But if you add this term, what this term actually does is starts kicking the ellipse at every orbit, making it precess. So it's going to be more like woo, 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 woo. We will see that because we will study the precession of the perihelion of Mercury and in general precession of periapsis. But this is telling you that, yeah, elliptical orbits kind of exist in general relativity, and the relativistic corrections kind of just kick the ellipse a little bit. That's kind of nice, that you can have elliptical orbits or almost elliptical orbits in general relativity. That's nice because the solar system can continue existing. Nice. Imagine that Einstein arrives and the solar system is like, dude, I need to go then. And then it disbands. No, not really. Elliptical orbits are of course present in general relativity. Right. Now, we can also study another kind of orbits that also have a Newtonian analog. That is the one where you enter with this amount of energy, say, like this. This amount of energy. So what is that? You come from infinity, then you hit the potential, right, barrier, and then you bounce back. So what kind of orbit is that? You don't have enough energy to overcome the potential. What kind of orbit is that? Something like this. So you go in a collision trajectory with the potential, then you reach a minimum radius, and then you bounce back to infinity, So this is a hyperbolic trajectory. Well, the analogous to a hyperbolic trajectory, of course, modified a little bit by the fact that it's fully relativistic, but this is what in Newtonian gravity, Newtonian orbital mechanics would be a hyperbolic trajectory. Now, in Newtonian mechanics, you see that as you increase your energy, what you would get is just hyperbolic orbits, right? If you increase your energy, you get hyperbolic orbits where you get closer to the surface of the planet, if you want, closer to the source of gravity. But it never does anything like that. If I increase energy, I'm just gonna bounce off the potential no matter what, no matter how much I increase. That is not what happens in general relativity, though. Let's see two cases of orbits that do not exist in Newtonian orbital mechanics. First of all, you could be here at the maximum of the potential. So that would be an unstable circular orbit, that you can tell. You can be at R0, but the problem is that any perturbation will either push you that way, and we'll see what happens when you're pushed that way, or push you this way, and then you will go all the way to infinity. So unstable orbits do exist in general relativity. Of course, they're unstable, so you will not spend much time in one of them. Now, most interesting is what happens when you have more energy. What happens if you enter with this amount of energy from infinity? Well, if you do, what's going to happen is that nothing stops you. If you were Newtonian potential, yes, you would hit here and go back. But this is not Newtonian orbital mechanics. If you get too close to the planet, this relativistic term starts to dominate, and it tells you that, well, once you cross this maximum, you're not going to go back. Not going to go back ever. There's nothing here to stop you and reflect you back, so you're not going back. You are getting in. No matter, I mean, again, this is the scale of the Schwarzschild radius, so this model of orbital mechanics stops working. We need to check what's going on when that happens, right? But you can tell that in any case, you're not gonna go out. If you come in with too much energy, you're gonna crash into the unknown, at least until we talk about black holes. Anyway, you can tell that, of course, for most planets, the surface of the planet is much further to the right than the Schwarzschild radius. But if not, well, what's gonna happen with you is interesting. So, we can discuss, and we will discuss about it later on. But for now, these are the cases. These are the cases of orbital mechanics, and these two last orbits are the ones that don't have a Newtonian analog. Now, so as a summary, we distinguish three areas in a way. We have, well, the circular orbits and all the stable orbits that live here, right? You can have stable orbits here. You have one unstable orbit, and then you have the scattering region in between, this area, where you would bounce off the potential and have a hyperbolic-like trajectory. And then everything above, where you actually would fall and never come back. It's kind of super nice to be able to express this potential as a Newtonian part plus something else and see the differences, isn't it? All right, let's check what happens with light, because this is for massive particles. We've assumed that we have a proper time, and the for velocity of it is normalized to -1. We know that the for velocity is normalized to -1 because it's a time-like vector, and trajectories of matter, right, of massive matter, follow time-like action, and trajectories of massive matter are time-like curves. What happens if the trajectories are light-like curves? What happens if we're talking about massless particles? We're talking about lights, for example. Oh, well, then things are slightly different. Let's see. All right, so for massless particles, there are differences though. For massless particles, we know the tangent vector, the for velocity. We cannot parameterize in terms of proper time. We have to parameterize with respect to some affine parameter of the trajectory. Let's call it S, right? It doesn't represent proper time. There's no such thing as proper time from light particles, for photons, if you want. They are kind of eternal. They see the beginning and the end simultaneously, if you want. Again, it makes no sense to talk about a notion of proper time for massless particle. Now, for those massless particles, though, we can still define a for velocity with respect to some affine parameter, right? That parameterizes the curve generated by the velocity, the for velocity of that curve. And then we can write, again, the normalization of the for velocity. But realizing that now the tangent vector is a null vector, and therefore the contraction with itself, the square, if you want, is equal to 0. So I do the same as I did before. I do this contraction and I equate it to 0. Now I do the same again, same as before. So theta is pi over 2. This thing becomes a 1, right? Then the L quantity becomes r squared phi dot. Then this one goes to 0 as well because it's constant theta and on the equatorial plane and don't leave it. And inserting, same as we did with the time-like trajectories, inserting the two conserved quantities in here to substitute t dot and to substitute phi dot, I end up with this equation. And this equation can also be written in the mechanical energy kind of form, with the potential in this case being this. Now, this potential is very different from the potential for particles. We can plot it and then see what kind of orbits we can have for light. The curve looks like that. So r, v of r, for r going to 0, the negative term that you get from the r cube here is going to dominate. And for r really, really large, this is going to be killed completely. So there's a maximum, and it's in that sense, you see that there's no region at all for stable orbits. So light or massless particles have three things to do. Either this, enter with this energy, which is bouncing back. So you would have a hyperbolic orbit for light. Light would come and light would go. You would have maybe light here, and that is it's actually the position of this is 3dm. That's what we call the photon sphere. So that tells you that photons in principle could orbit something massive. Actually, anything that can be orbited like this, it will be a black hole. But let's not get into that. Let's not get into that because we haven't talked about black holes. I will give you a hint at the end of this section. Now, the 3GM, I will give you a hint at the end of this video. At 3GM though, you will be able in principle to see your neck, right? Because light describes closed orbits in a way, if you were able to stay there. However, the orbits are unstable, so photons would not keep orbiting in the photon sphere. It would either go inside or go outside. And of course, if they go outside, they go all the way to infinity. If they go inside, they actually fall into this category. So light that enters with more energy than the maximum of this potential will never come back because nothing will stop it. So light doesn't come back. It's very black, that object. Now, interesting enough though, something that can sustain a photon radius will not be able to sustain stable orbits of matter around it. So this thing has to be a black hole. Matter cannot really orbit. Matter will end up collapsing into whatever it's falling. So yeah, there cannot be stable orbits of matter anymore. We will talk a little bit about that when we talk about black holes proper. So we've seen that light indeed can be bounced back by a gravitational field, by the gravitational field of a planet. That's not surprising, it happens in Newtonian mechanics too. There's also room for an unstable orbit. And after that, you have energies above which there's no way to come back for light that is going to collide with the planet gravitationally. And again, planet is definitely not the name you should use for that object if you get to an extreme where you can actually cross this with light. We're going to continue to see particular applications of this orbital mechanics. We're going to see gravitational deflection of light, the first test of falsifiability of general relativity, and the precession of the perihelion of Mercury, which was actually the first postdiction of general relativity. All right, the next thing we're going to see, now that we've computed the orbital mechanics, the possibility of orbits for massive particles and for light, we're going to see two applications. The first of them we're going to see is the precession of the periapsis. And in particular, we will particularize the case of Mercury with the Sun. So let's understand a little bit what we're going to do. We're going to sketch how to solve the equation of motion for a planet that is orbiting a star, right? So we know that equation of motion is like this. We already saw it. That's the equation of motion for a massive particle, right? So following time-like trajectories, time-like geodesics. I have this equation where V is this potential, right? And this potential that I have here, remember, this part is the relativistic part.
Relativistic. And this part is, if you want, the Newtonian one. Okay? So,
what we're going to do is we're going to make use of the conserved quantity L. The conserved quantity L, when we are in an orbit in the equatorial plane, that we can always assume without loss of generality that we are in the equatorial plane, then we know that L is equal to r squared phi dot that we saw just right before. That means that phi dot minus 2 is equal to r to the power of 4 divided by L squared. Now, in this equation here, we're going to do the following manipulation. First step to operate with this equation is to multiply by phi dot to the minus 2, which is the same as multiplying by r to the 4 divided by L squared. I can choose which one I multiply by because it's the same. So on the left-hand side, I'm going to multiply by phi dot to the minus 2 here. So that gives me
dt d phi square multiplying dr dt square, and that's of course the same as dr d phi square, right?
So that's what I have on the left-hand side. And on the right-hand side, I multiply by r to the 4 divided by L squared. So r to the 4 divided by L squared. I just put it would be r to the 4 divided by L squared, but I put this into the denominator of the denominator. All right. So what we do now is we're going to implement a change of variables. We're going to change for the variable r to the variable x. With this particular change of variable, that would be pretty useful. The change of variable, of course, tells me that 1 over r is gm over L squared x, and also that the derivative of r with respect to phi, using chain rule, gives me dr dx, dx d phi. dr dx is minus L squared over gm, 1 over x squared, and that multiplies dx d phi. Okay, so I did that change. On the left here, I did the change of the derivative. I did this change here. And on the right, every time that I saw a 1 over r, I substituted by the value gm over L squared x, and gives me this factor here. Arithmetics and substitution here. All right. Also, here I had the r to the 4, I also substituted here. We can simplify also this factor with this factor, giving me an overall common factor L squared over g squared m squared, multiplying all this. Now, of course, I can simplify all this, right? Because this factor is equal to this one inverse, it's equal to this one inverse, simplifies quite a lot. And arithmetically simplifying, I get this equation in the end. Now the next thing we're going to do for convenience is differentiate again with respect to phi. I take a second derivative, another derivative with respect to phi on both sides of the equality, here and here. So the result, to compute this result, I use that the derivative with respect to phi of dx d phi squared is twice derivative of x with respect to phi, second derivative of x with respect to phi. And the same way, the derivative with respect to phi of x to the power n is m, derivative of x with respect to phi, x to the power n minus 1. Using that, we obtain this equation here. All right, but this equation can be simplified, factors 2 can fall everywhere, and it yields this equation here, after simplifying. Second derivative of x with respect to phi, twice, minus 1 plus x equals 3 times g squared m squared over l squared, x squared. And this is the equation, this is indeed the equation that the orbits will satisfy in general relativity. Notice, though, that this term can be traced back all the way to this term here, which is the relativistic term. And the relativistic term is precisely what makes this a non-homogeneous equation. And the relativistic term is precisely what makes this non-zero, the right-hand side of the equation. So the Newtonian analog to that one, and I write with an x0 to make sure that we understand that there's different solutions, this would be the equation that the Newtonian orbits would satisfy. And this is the equation that relativistic orbits would satisfy. So now we're going to copy these two equations to the beginning, and we're going to sketch how to solve them. I hope that this is clear. By the way, this is up to here, no approximations have been made, not at all. Everything is exact. This is the true equation of motion, of course, on the variable, instead of on the variable r, on the variable 1 over r, because it's more convenient to write it like that. So this is the equation of motion that orbit would satisfy in GR. And this will be the Newtonian analog. Okay, let's copy them and put them up here and attempt to solve them. All right, so we have the equation of motion here for the orbits, and we're going to solve it using techniques from perturbation theory. I will tell you when I'm doing approximation. So far, this is exact. Now I'm going to make an answer. I'm going to say that the solution is going to be the sum of a solution to the Newtonian equation of motion plus something else that makes the difference between the solution to the Newtonian problem and the solution to the full relativistic problem. All right, so what do we do next? What we're going to do is we're going to insert the ansatz into the equation. If we insert the ansatz into the equation, we get the following. So all that I did is use the linearity of the derivative and then substitute, when I see an x, I write x0 plus x1. Now, you may think, what have we won with this? Well, we have won something because this thing here is the equation that we know it's equal to 0 for Newtonian orbits. So we know from the fact that the Newtonian orbit equation is this one, and we know that for the Newtonian solution this is 0, and by definition my split is between the Newtonian solution plus something else, plus the relativistic part, if you want. So this thing is actually equal to 0, identically. So that thing I can cross out. All right, so what I have now, it's something, there's an equation combining x1 and x0 plus x1. Now, I want to solve for x1. What I want to solve, let me just write it. Let me just write it here for comfort. So you see that now we have an equation on x1, an equation on the perturbation, if you want. Again, no approximation have been made. So far all that I'm saying is writing the total solution as the Newtonian solution plus something else. Okay, the something else is what relativity brings to the table. Now, in writing this, I have this equation for the new things that relativity brings into the table. Now, the problem is that this equation is still too complicated because it's not linear, because of the freaking x1 squared. Now is when we're gonna start doing approximations. We're gonna approximate that the correction, because we're gonna talk about planets that are not too close to a neutron star or something very extreme, we're gonna assume that the relativistic correction, the relativistic change to the solution, what relativity brings to the table is small. So we're gonna say that x1 is going to be neglected when added to x0. Okay, every time you have a sum of x0 and x1, you neglect the correction because it's going to be small. But if you do that, this simplifies quite a lot. So that means that the second derivative of x1 d phi squared plus x1, it's equal to, or approximately equal, we should say here, at leading order, to 3g squared m squared over l squared x0 squared. So now that is an easy equation. Why is it an easy equation? Because now this equation is linear. It's a linear second order linear equation with inhomogeneous, sure, with an inhomogeneity. But it's linear because the unknown here is x1. Okay, so now if I know the solutions x0, I'm going to know the solutions to the full problem. And I happen to know the solutions to x0 because I know the solution to x0 is the Newtonian problem, and this is the equation for an ellipse in the variable 1/r. So let's write down the solutions to the Newtonian equation. Let's call it n, and then we write here the solutions to n. Like this. These are the solutions. This thing here are the solutions to the Newtonian equation that we know. This is the equation of an ellipse on the variable 1/r. In fact, I can solve it for r0, and we get the more familiar equation for an ellipse, where the e is the eccentricity of the ellipse. Actually, if we draw it, we see here, this is the radius. This is the radius as a function of phi, and as a function of phi, the radius increases. The radius is minimum when you're the closest. When the cosine is equal to 1, that makes this denominator the largest because the eccentricity is a positive number. And then when the cosine is -1 is when you get the largest radius because the denominator is the smallest possible. So this is when the cosine is equal to 1 is pi. So this is the point of being furthest away, right? When phi is pi, and then you go again back to phi 0 to pi, which is the same the cycle makes, and then the whole thing, the whole trajectory, as you can tell from here, is an ellipse. It's an ellipse. The radius is getting closer and further as you change phi. To check that this solution is correct, you just need to plug it in or just solve it. This is a very simple second order linear equation with an inhomogeneity, right? So you can solve it. But if you don't want to solve it, this is the solution that gives you that at phi equals 0, you are the closest to the center of gravity. All right. So ellipses, Newtonian ellipses, and like this. Wonderful. So I know then that x0, I can plug it in here, and I would get the solutions up to leading order in this factor, in this multiplicative factor. Okay, so let's substitute the value of this solution in here and try to solve what would be the leading order correction x1. This is the equation, just plugging in the solution in here. Now this equation we know how to solve. It's again a linear equation that is just non-homogeneous. It's got an inhomogeneity. Alright, it's a second order linear equation that I know how to solve with an inhomogeneity. And we solve it, and the solution, let me just write the solution, is this one, where I already added here, I wrote actually x0 plus x1, okay? I wrote the two x. Now, this is the solution at leading order in this perturbative parameter. So this is...
At leading order in d squared, m squared divided by l squared, okay?
So this is the leading order correction. It's not exact, it's the first order correction. But if we're talking about planets around stars, we assume that the field is not too strong, as we discussed already in the videos. And let's compare the two solutions. If we compare the solution here with the solution here, we notice something. Remember that the perihelion, the periapsis of the orbit would happen at phi equals 0. Because at phi equals 0, you see, I mean, you can tell already from this. I mean, you can tell in this form, of course, easily, but you can tell already for this. This thing is periodic over 2 pi. When phi goes to 0 to 2 pi, you go back to the periapsis. However, with the corrected solution, I got this. What does that mean? Well, I do start at 0, but when I move to phi equals to pi, I'm no longer at the same point I was before. You see, I'm missing a little bit because I'm multiplying by a number that is less than 1. That's it. After a full orbit, after I complete the 2 pi value of phi, keep in mind that I'm going back to the original starting line, but I don't get to the perihelion anymore. When I get back here, I'm no longer the closest in the orbit. So I don't get to the closest point, to the perihelion again, when I advance to pi. Instead, the perihelion has advanced. In order to get to the perihelion, I need to move a little bit more. I need to add an extra angle here of 2 pi times 3 g squared m squared over l squared, because I'm subtracting that from the argument of the cosine to go back to the perihelion. Now, you see, what would that imply? So that implies that in the orbit, let me just draw it here, if I do a first orbit that is like that, when I come back, I move a little bit the perihelion. And when I come back, I move a little bit the perihelion. When I come back, I move the perihelion. So this is the precession of the perihelion of the orbit. My drawing skills are like BS, so don't take it from me, but this is what's going on. The whole thing, the orbit is being, the perihelion is being moved like this. Follow my pen with a drawing, right? Like that, like this, and the orbit does that. The perihelion advances a little bit after every orbit. All right, so the leading order correction, the leading order relativistic correction to the orbit of a planet around a star is a precession of the perihelion or the periapsis. I'm talking helium, that means it's the sun here. But in general, for any orbiting body, we'll talk about the periapsis. So the closest point to the gravitating body in the orbit. Now, we can apply to Mercury. And why would we apply to Mercury? A little bit of history. When in the time that Einstein was developing general relativity, there was a very well-known problem, that is the problem of the precession of the perihelion of Mercury. What is that? The precession of the perihelion of Mercury was an astronomical observation that didn't match Newtonian predictions. How is that? Well, it had happened in the past. So you look at the orbits of the planets, and then you predict where the planet should be at some time, and then you realize that the planet is not what it should be. It did happen in the past. It happened, for example, with the planet Neptune. Actually with Uranus. With the planet Uranus, what it happened is that as the planet was orbiting, they tried to predict where the planet should be at a given time, and the planet was not quite what it was supposed to be. In the orbital parameters, it didn't quite coincide. They said, Newtonian gravity is failing, and they thought, no, there must be another planet that we can't see that is perturbing the orbit. And then they computed, okay, there has to be a planet of about that mass in that position. And they looked at that and they found Neptune. So that is like, wow, look at this falsifiability prediction of Newtonian gravity. It predicted a planet that nobody had seen before. Very cool. So Newtonian gravity was solid. Now, something similar happened to Mercury. Mercury, the orbit of Mercury, the perihelion of Mercury was precessing like this. And was precessing, and they said, that must be the three-body correction coming from the influences of other bodies, as in like Jupiter and other bodies of the solar system. And they computed that influence, and they found, no, actually that accounts for about half of the precession of the perihelion of Mercury. Where's the other half? And that was another problem, and they theorized, there must be another planet. But the planet has to be too massive and too close to the sun. It's not supposed to be stable, being so massive so close to the sun. We can discuss why if you're interested in the live sessions. So, nobody knew what the answer would be. They still said, no, there must be something a planet. Newtonian gravity has to be right. Now, when Einstein started talking about relativity, there was a person, Eddington, in Cambridge, in the UK, that was tasked with actually debunking Einstein. People in Cambridge were not very fond of Einstein, because he was kind of saying, no, Newton wasn't quite right in many ways, and England and Germany weren't at the finest of relationships back in the day. We're talking World War I times, okay? Now, Eddington, in the end, studying relativity, became convinced that there was something to it, and Eddington actually asked a question to Einstein. Can you check what your theory predicts for the orbit of Mercury? Because wouldn't it be great if it predicted the exact value that they're missing for the precession of the perihelion of Mercury? And the value that they needed to predict was this one. First, the angular momentum square of an elliptical orbit. A is the major semi-axis, so it's G-M-A times 1 minus eccentricity squared. I substitute this in the expression that I had, and when Einstein did the numbers, guess what Einstein got? And surprisingly, perhaps, it was definitely a surprise, Einstein nailed it! Started a long streak of nailing things. Einstein nailed it and got the precession of the perihelion of Mercury exactly the amount that astronomers were missing. How is that? That alone, that response is what convinced Eddington to do the experiments where they saw gravitational deflection of light as predicted by relativity, which is the next thing that we're going to compute. But there you go. The precession of the perihelion of Mercury, an open problem in Newtonian gravity, if you want, was accounted for by the relativistic calculation, in particular by the leading order relativistic calculation, which is enough to explain for something that is the Sun and Mercury with the field is not really that strong. All right, let's take a look at the gravitational deflection of light. All right, so this is a problem that was the first falsifiable prediction of general relativity. Einstein predicted that during an eclipse, there's going to be a star that shouldn't be seen. If Einstein's theory was not correct, the star should not be seen if we go with Newtonian gravity. But if general relativity was correct or get correct predictions, you definitely should see the star, because the star was behind the sun and the deflection angle. So if you want, this is the star. There was no direct path to the eye here on Earth, right? This would be an eye. Or whatever, just, my goodness. I don't know, and just that. So light would go that way, but then would be bent and go to the eye. Now, one thing has to be said. A common misconception is to say that Newtonian gravity predicted no deflection of light by gravity. That is not true. That is not true. Newtonian gravity does affect and curve the rays of light, the propagation of rays of light. So if you have heard that Newtonian gravity light doesn't curve, I think it is because people think of general relativity as curving space-time and Newtonian nothing like that. So therefore, how can it be curved if it's not relativity? No, Newtonian gravity does predict that light gets deflected with a scattering angle. Light changes angle when it's deflected by a gravitational field. If you want to see a calculation with Newtonian gravity, you can check this reference that I will of course also link in the comment of the video. All right? Okay, now back to our problem. Similar to the previous exercise, we're going to make the substitution. L squared equals r to the power of 4 d theta ds squared. Now that substitution again comes from assuming that the orbit is in the equatorial plane, that we can do without loss of generality. All right, so multiplying this equation, if you want, by d phi ds squared, we get this thing. I will get d phi dr squared, and this thing is going to be, well, I multiply by L squared divided by R4. If I expand it, I get this. Of course, I get a square here. I undo it with a square root, and I get two branches of solutions. Now, the two branches are important here, so I can get a plus minus, because for this particular problem, I need both. Let's see why. Okay, so here we have a typical scattering diagram, and then we see that I call phi, let's say the angle from, let's say the horizontal one, and I call the origin of phi this point here. So what I do here, I have a point of maximum approach in the scattering, so the ray of light comes from infinity, gets to a closest approach, and then is scattered away. Now, we have the angle at the entrance, right, at r infinity, what is coming in, and that angle, you can tell that that angle starts increasing. As I decrease r, the angle increases to the maximum, which is pi. You see here the angle is pi at the point of maximum approach. So the angle is actually increasing. This is the instantaneous angle at this point, and it usually goes all the way and it's pi over here. So you can tell that as I decrease r, the angle increases. This is the negative branch of this. The derivative of phi with respect to r is negative. And in this branch, now, as I increase r, phi is increasing. So at this point, the derivative changes sign. When I increase r, I increase phi. Phi keeps rotating. You see pi and then more than pi and so on and up to here. So phi keeps increasing as I increase r. So in this branch, this is the positive branch, right, of the derivative, and this is the negative branch of the derivative, and that's why I wrote there. Let me just write here positive for reference. Okay. Now we have the positive branch here, the negative branch here, so we have to be careful when we integrate the right ones. Okay. In the scattering problem, we move from the negative branch. As I increase r, you see the angle decreases from pi to less, and here as I increase r, the angle increases. All right. So now that we know that, let's compute the angle of scattering based on this expression that we have here. All that we need to do is integrate. All right. So what I did is I got, of course, the delta phi is equal to the integral with respect to r of the phi dr between the points a and b, right? A variation of r, or r of a and r of b, right? So what we have here is we have from infinity to r0, from the point for r infinity to the point of maximum approach, with a negative branch following the negative branch of the derivative, plus from r0 to infinity again. This is r equals, this is if you want phi of r going to infinity again, following the positive branch. Okay, so we have these two integrals, and then these two integrals that have opposite sign can be rewritten as twice one integral, like this, by switching the integration limits and getting a minus sign. I combine it in two, and this integral can actually be evaluated analytically after doing a Taylor expansion, assuming the parameter GE over L to be much smaller than 1. Doing that, we obtain this expression and leading order, and this is for weak gravity again. For weak gravity, we obtain that this is the deflection angle. All right, we can evaluate what it is for rays of light that graze the surface of the sun, just plugging in the numbers, and then we would get this quantity. The dependence on the mass of the sun is encoded in the value of the geodesic constant E, the conserved quantity E, and this is the value that you would obtain after you substitute by the values for a ray of light grazing the surface of the sun. Okay, so this is twice what the Newtonian value predicted, and this is what Einstein predicted Eddington would detect. And Eddington indeed measured this deflection angle for the star that was visible when Eddington looked at the solar eclipse and saw a star that would have been more than half of this behind the sun, and then suddenly when you looked at it you would see it over the sun because the gravitational deflection of the ray of light, a ray of light that should not have reached your eye because it was deflected towards your eye by the sun. So a proof that sun curves space-time in a particular way that Einstein predicted with general relativity. Alright, this is the last exercise that I wanted to see in orbital mechanics. With this we're going to end this video. In the next video we're going to do hopefully a fun exercise in orbital mechanics that was actually a sample of a final exam, again the first time I taught general relativity. It's going to be, I hope, a really fun exercise, and Newton, Stephen Hawking, Emmy Noether, all of those characters will appear. I will see you there, and until then, take care.